Hello. Hello. Okay, so there's supposed to be some delay in the transmission. So if I ask a question, I know that I'm not going to get a response immediately, but maybe if there is anyone out there, you can wave your hand somehow. What it shows on my side is current viewers 1. That's possible, I guess. I'm not even sure if it's myself or not. Let me just check the WhatsApp. Maybe anyone has written something in there. Okay, so the Chad posted another link. I guess Chad is out there. Are you there, Chad? Yeah, this is the first time for me as well, so I'm not really sure how it all works in practice. Okay, so I guess we should get started. It's already 3 minutes past 5. Oh, there we go. I can see some comments here. Hello, everyone. Hello, Ubaidullah and Chad and Graham. Great. My YouTube live session still shows only one viewer. I guess it doesn't update. So I'm just going to ignore that. Okay, so the plan today is for us to do some mathematics. Well, first of all, I just want to make sure that the voice is right. So can you, well, I suppose you can hear me well because I've got my microphone on the top volume. What about the music? Is it distracting? Can you hear a loud music or something like that? So I'm going to put the music quiet so that it's like in the background, but it doesn't distract our thinking. Okay. Okay, so the first rule is that any request that you have, you can just put it on the chat, or you can put it on the WhatsApp. And these can be the requests for us discussing some mathematics here. Oh, an echo. Oh dear, that's not good. Let me see. Maybe this will help. Is there still an echo? Is it better now? Is the microphone better now? You can post your answer on the chat, please. Okay, so some instructions. Well, first of all, let's get to know the interface. So this is a little intro I prepared here. What you see on the top right corner here is the graph of a function, which is being played in the form of a sound. So you can see how mathematical classical music can be. By the way, it is not an ordinary function whose values are real numbers. Here the values are sets of real numbers, because you see you can have multiple values for each x value. There are multiple y values, and so it's a function from reals to sets of reals. Okay, then we've got a color-coded vector field. You know, on R square, if you've got a function that assigns to each point on R squared a vector, that's something like that is called a vector field, and you can color code it. The color could be representing the direction of the vector, and so you've got a color-coded vector field there. And then there is some mathematical terminology like mathematics and live or live, which has this double meaning. Okay, so then there is blackboard. That's the thing that's black, and underneath there, somewhere behind there on top, there are some sound waves. These are the things you're hearing in the form of my voice as well as the music. Okay, so that was just the intro to the interface. By the way, okay, so with the music, the point I want to make there, apart from the fact that music can be relaxing, the point I want to make there is that mathematics is everywhere, and doing mathematics doesn't necessarily mean that you're in that technical boxical environment where you're isolated from all the other aspects of life. For me, doing mathematics is submerging in every aspect of life, and we can experience mathematics not through only our brain, but through our sensations as well, like we can do with music and with art and so on. So that's the symbolism behind having that background music. Okay, great. So any topics on request for us to discuss? There is nothing on WhatsApp so far. If there will be no topic, then I'm going to choose one on my own. I haven't prepared anything though, so I would much prefer if at least in the beginning there is some request. Okay, first of all, let me check if the blackboard works. Okay, so let's draw a little flower here. Great, it seems to work. Okay, good. Any math requests? Nothing coming in so far. But I can also see that the delay is quite significant. Maybe more than 20 seconds or so. Okay, well, so far, I'm sure all of you there are engineering students, so we're going to be doing some engineering mathematics. Oh dear, I just received a request. Well, I actually said that if I receive a request on WhatsApp, I'm not going to reveal the author of the request, so maybe I should stick to that. But I received a very daunting request, which is to discuss eigenvectors in real life. And I must admit that I'm going to fail immediately, because I actually have no idea of the practical applications of the theory of eigenvectors, because I'm very ignorantly not an applied mathematician, although I made a whole story about living mathematics. So unfortunately, this is something that one of you will have to investigate through the internet or other means, and then join me on the YouTube session, and then you can share your experiences on that. I really have no idea of applications of eigenvectors in real life. But you will encounter lots of them in your engineering studies. I'm quite sure of that. Well, one thing to say there, which maybe could also serve some kind of introduction to the next week's work, is that so here's a possible application in animations, 3D animations or 2D animations on the computer and things like that. So if you've got a Cartesian plane and you're transforming your plane, so you might be rotating it or doing some other kind of transformation. Well, imagine if it's like a 2D plane, then things are not so difficult, but if it's like a higher dimensional space where you want to take into account a lot of factors, not just the 3D position of a point, but also other characteristics of it and so on. So it becomes a higher dimensional space. And then certain maneuvers in space sometimes lead to transforming your space in a linear way so that it's given by a matrix. But then it can become very difficult to compute the values because matrix can be huge. And so if you manage to show that you can find an alternative basis for your space, let's say we found another basis which is given by this orange pair of lines, in such a way that for this alternative basis, if you now express all your vectors in terms of coordinates for this orange basis, then the transformation that's described by a matrix is given by a matrix that's not any more so complicated, and in fact you can get sometimes that matrix to be a diagonal matrix. So by describing transformation of your space using an alternate basis, not the one that's given by the x and the y axis, but an alternate basis like the orange one there, you get to describe your transformation as a simpler matrix, and specifically as a diagonal matrix. And so this is the orange matrix you get then out of the initial white matrix that was describing the same transformation relative to the old basis, the white lines there. And so the white matrix was given by certain values, but now the orange matrix has the diagonal entries to be only the non-zero entries, and the others are zero. And so the question is now how to find this new basis and the orange matrix with the diagonal entries. And it turns out that all you have to do is the following. The A and the B are going to be the eigenvalues of that old white matrix, and these new basis vectors, these ones, will be the eigenvectors. Yeah? So, and it shouldn't be kind of surprising, because if your transformation, if all it does, it stretches these orange vectors, then let's see what's going to happen to everything else. So let's say the transformation, let's pick specific values now for A and B. So let's say that the transformation stretched the first orange vector, and now I will have to label them. So let me call this the capital X and the capital Y, whereas the old basis vectors were called small x and small y. So let's imagine they're unit vectors. And so if my transformation behaves in such a way that the vectors lying on the orange lines, they get stretched. For example, this vector, the blue vector there, got stretched by a certain factor. And so let's draw the stretched version of it with darker blue, okay? And that lighter blue thing there got stretched by another factor. So that's the factor A, which now maybe we can have it to be equal to 2. So the factor by which the light blue vector got stretched, and the other one maybe it's equal to 1.5. Okay, and so it got stretched here. What will happen to the rest of the vectors? Well, because a linear map preserves linear combinations, the rest of the vectors will dislocate according to these stretchings that occurred here, right? So, for instance, if I had a vector that was the sum of... okay, so I just received a request to revise something that's going to carry a lot of marks in A2. We're going to do that right after we finish this discussion. So if, for instance, we've got this vector here, because the x vector got stretched by a different factor from the y vector, the vector, their sum is not going to get stretched. Their sum is going to dislocate a little bit, okay? And so the effect of this will be just multiplying those vectors by the orange matrix if we are in the right coordinate system. But now if we go back to the white coordinate system, there was no way for us to tell what was going on here. Like some vector moved a little bit. You see this white vector moved a little bit to the right and then got stretched. So there's no way for us to kind of conclude that something much more simple is going on, like multiplication by a diagonal matrix. So by finding the eigenvectors of the matrix A, we are able to find a different coordinate system for the same space in which we can express the transformation as multiplication by a diagonal matrix. And so that's leads to very useful applications where computations can be simplified significantly. But again, it's like a speculation and application potentially at a theoretical level. So unfortunately, I cannot tell you exact real-life applications of these things because I don't have enough knowledge for that. If I was an applied mathematics lecturer, I would be able to talk a lot about these things, but not when I'm a mathematics lecturer. Okay, so that answers, I hope, well, it doesn't really answer, but at least it partially addresses the first request I had here. to talk about some practical applications of the theory. By the way, we are going to be looking into this next week, and specifically what we're going to do there is that we're going to be given a curve like something like this, and okay, I've got a question there about the previous view, so let me go back here to answer the question. Does it mean, so I'm reading out the question, does it mean that the orange coordinate system, you can only describe that basis along the two lines? Orange coordinate system is the basis, it is that new basis. And the orange vectors, of course, they're not, okay, so the white vectors have coordinates 1, 0 and 0, 1, right? The orange vectors relative to the white coordinate system don't have such simple representation anymore. Sorry, there should be 0, 1 there. Yeah, if I look at the x and y coordinate of the orange vector, it has some non-zero values. But now, if I take this blue vector, for example, in the white coordinate system, it looks something like RS, right? But in the orange coordinate system, the blue vector has coordinates, the dark blue vector has coordinates 2, 0. Because the blue vector lies on one of the coordinate axes for the new coordinate system. Okay, so just to make sure I did address the question, let me go back to the question. So the question was asking, does it mean that the orange coordinate system, in the orange coordinate system, you can only describe that basis along two lines? I'm not sure I fully understand the question, to be honest. I've tried to answer as much as I thought I understood it. If you want to make your question a bit more precise, I'll be happy to look at it again. Okay, so the application we're going to be looking at the very end of next week will be that you'll be given a certain curve in terms of its equation, and you'll have to determine which kind of curve it is. Is it a parabola? Is it it will be one of the conic sections, either parabola, either ellipse, or hyperbola, and so on, but you will have to find out which. But because it's repositioned in a funny way, like this parabola, for example, if I write down the equation of it, the equation with the white coordinate system, the equation definitely will not be y equals x squared or anything like that, right? It will be much different from this. But now the question is, how can we figure out if I have an equation which in general will have the following form: a y squared plus bxy plus c x squared plus d equals 0. If I have something like that, how do I figure out which shape does it have? Is it a parabola? Is it a hyperbola? And so on. And so there's no way to figure out directly by looking at this, but what we can do is we can reposition the entire space by finding new coordinates for it, new coordinate system for it, and specifically for this one, what we will do, we will get this kind of coordinate system. And then if I transform this equation into the new coordinate system, it will look something like this: y squared equals x squared plus 5 or something like that, because the parabola is now shifted up. And once I transform it into the new coordinate system, now I can see what kind of shape it is by looking at the equation. It's a parabola. And so in all the effort of doing this, what you will have to be figuring out is suitable eigenvectors and eigenvalues, so that then we can describe this transformation and then use the diagonal matrix I talked about in the previous view, and so on. So all of this is coming in next week's work. So that's just a little bit of practical application, I suppose. But real live practical applications, that's something that is not discussed in this course, and I've never looked into that, but there are lots of them. And maybe you should ask some of your applied mathematics lecturers, or you can also look on the internet and teach me about that, because I would be keen to know about those practical applications. Okay, so let's look at the next question. So in the order that it appears, the next question was that we perhaps could revise something that is going to carry a lot of marks in A2. Okay. So I'm gonna do that. Now, before I do that, I'm just looking quickly at the WhatsApp to see if there is anything new there. Okay, there is some discussion here on WhatsApp about marks, but I'm not going to enter into that. That's course convener's task to discuss these things with you. Okay, so let's look at some topic which could count for a lot of marks in an engineering mathematics exam. Well, I mean, surely you understand I'm not allowed to disclose any information about the exam. Not that I have any information about the exam. I actually don't have any information about the exam, except that I have experience of 10 years of teaching this course. So I'm not sure how reliable my answer to the request will be, but I'll still try my best. Okay. Okay. So let's see. What will count a lot in an exam? Well, I suppose those things that counted a lot in terms of the amount of work during the semester. And so do you want us to look at something in the second term or the first term? Maybe Ubaidullah could clarify that if you want us to look at something from this term or from last term. But meanwhile, definitely one of the big topics here that we're discussing this term is the topic of eigenvectors and eigenvalues. And I think perhaps all of you that are listening here, this is already quite clear, but maybe I should still point out a tricky point there. And namely, okay, there are two tricky points that I could see there, which might result in deducting a lot of marks if you're writing this on an exam. So when you're solving for eigenvectors and eigenvalues, and when you simplify your matrix, so you remember the one that has, okay, so let's begin with an example actually. A equals 2, 4, 5, 4, 3, 1, 5. I'm not going to solve this example completely, but we're going to talk a little bit about it. Okay, so Jamo Soko is asking, how am I doing? I'm doing great. Thank you very much, Jamo Soko. I hope you're doing good too. I know that it's been a difficult time for everyone, and I mean, all these things going on with the virus and all of that. But let's try to keep positive, and I've been certainly trying to make most of the opportunity that the online teaching provided. It does mean that I'm spending now, I think, 3 times more time than I would have spent on delivering the module. But at least I'm creating some material that can be reused in the future as well, like those written lectures and so on. Okay, so let's go back to mathematics. So the matrix A, let's say we got a matrix A like this, and when you solve it for the eigenvalue, you know that you need to do this thing that when you take the determinant of that matrix, where you subtract lambda from the diagonal entries, and so you get something like this. By the way, if at any point you have a question about any of these steps, do point them out on the chat. Okay, so then you solve this determinant, you equate it to 0, you find the lambda, then you put the lambda back into the matrix, and then you solve the system of linear equations, and the system of linear equations you solve will be of this form for each lambda that you found. And the tricky part there that I wanted to talk about is that when you simplify the system, and you get it into this row echelon form, so I'm not going to do that now because of its of the length that it will take in terms of calculation time. But I mean, unless you want me to do something like that. So when we simplify this and we get some numbers here, let's say we get the following numbers. Let's say we get here. So this is hypothetical. By the way, I forgot to introduce you to my friend. He helps me with thinking and making sure that everything is right. So where is he? Let me try to find him. Here we go. Somehow he disappeared. Okay. Oh. I think he's back now. There we go. Alright, you don't see him yet, but you will see him very soon. Oh, you see him already, I think. Good, great. So that's my friend. He sometimes helps me to think about things. He doesn't spot those errors, though, that I make often. Anyhow, so we get a certain matrix here which has some values, and let's say we have values that are of the form 3. So this is hypothetical. So this is not really true. Maybe I should indicate this with a broken line there. So let's say we get a 3 there, and some 5 and some 7, and here we have a 0 and 2 and 8 and 0 and 0 and 1. Okay, first question. Well, I haven't prepared for any prizes here, but if I had any prizes for you, then it would be a prize-winning question. Can we ever get a matrix like this? Okay, so chat says that he will spot my errors. Good. So tell me then, could we ever arrive to a matrix like this when we're trying to solve for an eigenvector? I'm gonna have to wait a little bit more than you'll take time because of the delay in the communication. So I'll let you think meanwhile. So why don't we take like a minute of thinking about this? So the question is, can we ever get a matrix in this form for finding eigenvectors? So chat says no, and I'm not gonna ask him why, because it's always long to communicate. I think what we should do, though, we have to organize a way for the participants to tune in the live stream, and then they can talk as well. So the reason why the answer is no is indeed yes, because you arrive to the zero matrix. So wonderful. Okay, so Katie and Leila also are saying no. So the only solution that oh no, sorry, Katie said yes, but maybe she meant no. The only solution that you will arrive to is gonna be 0, right? So if after the row simplifications you arrive to a matrix like this, then when you solve this for the eigenvector, you will only get solution k equals 0. And let's see why. Remember, if I translate this into a system of equations, it's going to be the following. So it's going to be 3k1 plus 5k2 plus 7k3 equals 0. And then here we have 2k2 plus 8k3 equals 0. And then we've got 1 times k3 equals 0. Indeed. Okay, so Arno now clarifies this as well. And so if you look at this, the last line here is gonna give you this line here is gonna give you k3 equals 0, and then there's gonna be this domino effect, right? So putting k3 equals 0 here is gonna give you k2 equals 0, and then putting those values there is gonna give you k1 equals 0. So it's impossible for us to get anything like this. Well, if we don't get anything like that, then what kind of thing do we get? And the answer to that is that we're going to have much more zeros than we typically get in Dro-echelon reduction, right? Because some of the things should, some of those k's should be allowed to be arbitrary value. Okay. Oh, by the way, it's actually a good idea. So if you want to ask your question more in real time without a delay, you can send it on the WhatsApp. It's going to be quicker than asking a question on the chat. I'm going to read out the question afterwards. Okay, so now that we understand we can't have anything like this, let me fix this up a little bit. So now imagine instead of this we have something like that, where I'm going to change this this still, where instead of, I'm just choosing my colors there. Okay, so instead of that 1 there, and instead of the 2 there, and instead of the 3 there, okay, we have zeros. Okay, so what if we have something like this? Then, so let's put here what if. What if we got something like that? Then we are going to so to see what we're going to get, we have to write down the corresponding system of equations, right? So it's going to be 5k2 plus 7k3 equals 0, and then we have here 8k3 equals 0, and the last equation says nothing. 0 equals 0, so we don't have to put there, right? Now this forces the second equation here, you always go backwards up, right? So the second equality here forces k3 to be equal to 0, and then putting it in the first equality, you get k2 to be 0, right? And so we get that k2, well, k1, okay, so that's the whole point. So what I was trying to explain now is that once we know that k2 and k3 are 0, what about k1, right? And so we know that k1 can be arbitrary real number except 0. And so then the eigenvector is, and here is another tricky point, because sometimes students don't know what to do here. So do we put it this way, or do we put the... okay, Rowan, I saw your request about the formula for the characteristic equation. I will definitely explain it. But before I do that, let me finish this explanation. So k1, 0, 0, do we put it that form, or do we put it in this form? And so we are now wondering here, what do we do, whether it's that, or should it be, should the answer be the following, where k1 is taken out completely, and we have k1 times 1, 0, 0, or maybe the answer should be in the form minus k1, 1, 0, 0, and things like that, right? So which of them? And the answer is all of them are fine. So the thing is that when you have an eigenvector, you don't have just one eigenvector. You've got a whole eigenspace of eigenvectors, and what you want is to find the basis of that space. So to illustrate it on a picture, let me draw the following. So with a 3 by 3 matrix, we're dealing with a transformation from r cubed to itself, right? So it's a transformation from r cubed to itself. And the eigenvectors of this matrix are going to be some vectors in r cubed that got stretched as a result of this transformation. So let's say this is an eigenvector. But now, if this one got stretched, what will happen to 2 times that? Well, because we are dealing here with linear transformation, so if k1 got stretched, okay, if k got stretched, then 2 times k will also get stretched. Why? Because stretching is a linear process, so stretching is multiplying by a. So if ak equals some lambda k, what's going to be a times 2k? Well, 2 will factor out, and it will be 2 times ak, and therefore it will be 2 times lambda k, and therefore it will be lambda times 2k. You see? Then the 2k vector also gets stretched by the same lambda factor. And more generally, if I've got a bunch of vectors that are getting stretched, their linear combination will also get stretched. And so the vectors that are getting stretched by the same factor form a subspace of the vector space, and the subspace is called eigenspace. And now in these answers, what we're dealing with here is a one-dimensional subspace, because you see, like for instance this vector k1, 0, 0, what subspace is that? That's all the vectors that lie on the x-axis, right? So if the axes are x, y, and z, right? And I look at the vector of the form k1, 0, 0, well, that will be a vector that lies here, whose y, you can see there, y and z coordinate are 0, and the x coordinate is k1. And so not just the single vector, but the whole x-axis will get any vector on that x-axis will get stretched by the same eigenvalue factor. And now the question is, how do we identify to an observer about that fact, about the fact that this transformation stretches all these vectors on this x-axis by the same factor? And we can identify this to the observer by either telling this person, okay, well, the answer is all of these vectors as long as k1 isn't 0, or we can just tell this person, look, it's this one that's the eigenvector. But now the person is intelligent, he or she knows that if something is an eigenvector, its scalar multiple will also be an eigenvector. So just giving him one eigenvector, you are essentially giving him the whole eigenspan this vector spans. Or you could present your answer this way, because this expression and that expression, they're identical expressions. These two expressions that I've connected with a blue line, they're the same expression. They have the same value. But this one is also fine because for every k1 that fits here, you can find another k1 that's going to fit there, and that other k1 will be minus the previous one. So let's say we had here 2. If we take k1 equals to 2, then to put it in the other form, we'll just take k1 equals minus 2, because then minus 2 together is going to give just 2, right? So as long as you're describing the same set, it doesn't matter how you describe it, and there are ways to describe it. One is to use a parameter, and it doesn't matter whether you use a positive or negative parameter. Another way to describe it is to give a basis of the space, and that's where you don't need a parameter anymore, and so on and so forth. So this is a tricky point here, another tricky point with eigenvectors. So the first one was identifying that because there is no conditions on k1, you want to have k1 to be arbitrary value. I've seen a lot in a lot of students' work in previous years, where in a situation like this, where they don't have any k1 value, they make k1 equal 0, and then they get a mistake, of course. And so the first tricky point there is to note that because there is no conditions on k1, it means there are no restrictions on k1, so k1 can be anything. And then the second tricky point is to know what it means to present your answer in terms of parameters or without them. So basically the difference between these two is the difference between eigenspaces and bases of eigenspaces. So you do want to read up on those concepts of basis and spanning and all of that, because they come into play here in terms of applying them in presenting solutions for eigenvectors, right? Okay, so that's what I wanted to say about some things that's gonna count a lot of marks in the exam, because if you get these calculations wrong, especially with mistakes that are of the form that show that you don't understand the concepts, and especially the concepts of vector spaces, you see the calculations you need to do here are kind of straightforward, to just do the matrix fun thing. But then after you do the matrix fun thing, you want to make sure that you got your answer in the right way. Otherwise, the marker is going to conclude that wait a second, you just know the methods of how to calculate things, but you don't really understand what's going on behind those calculations. So you're going to get deducted a lot of marks, and so that would cost some marks in the topic of eigenvectors. Okay, great. So now let me move to the next request there. Can you please explain the formula for the characteristic equation, where it comes from, or is it out of the scope of the course? No, it is not out of the scope of the course. I thought I explained it in my one of my video lectures. Okay, so it's actually quite simple. You got the matrix A, you got it equal to, well, the eigenvector problem is this, right? AK equals lambda k, and what you basically do here is you reorganize the terms here. You move the other one on the left hand side, and then you factor out a hidden ingredient from there, which is the identity matrix. Remember, the identity matrix times any matrix is going to give us back that matrix. So let's make a note here that this is the identity matrix. And so we can rewrite this thing here by replacing k with ik as ak minus lambda ik. And then you factor out the k, so that's equals to 0. And then you factor out the k, you get a minus lambda I times k equals 0. And this is a matrix equation which can be written out as a system of linear equations, where you get this matrix here, the matrix A minus lambda I, times the k matrix, equals 0. And so that's where you get the system from. And I'm going to come back to Katie Mee's question about the best way of simplifying the matrix in a moment. So you have a system of linear equations here, and then we know that a system of linear equations, well, if I write this out as a system, as an actual system, what's going to be the coefficient? So let's pick an example. Let's say the matrix A is 1, 2, 3, 4, okay? Then the system is going to, well, first of all, the A minus lambda I matrix is then 1 minus lambda, 2, 3, 4 minus lambda, and the system of equations will be 1 minus lambda times k1 plus 2k2 equals 0, and 3k1 plus 4 minus lambda k2 equals 0. And so when we have a system like this, remember we're looking for a non-zero k. A big warning sign there. We don't want k to be 0 because a 0 vector is not an eigenvector. And so we want to solve the system by finding a non-zero solution to it. And there is some fact from systems of linear equations that you would have learned previously, that such a system has a non-zero solution if and only if the determinant of the coefficient matrix is 0. And so the coefficient matrix is exactly this matrix A minus lambda I. So we want this determinant to be 0. So the characteristic equation, the determinant of A minus lambda I is 0, comes from the fact that we end up, in finding an eigenvector, we end up solving a system whose coefficient matrix is the matrix A minus lambda I. And then we want a non-zero solution to such a system, and the non-zero solution exists if and only if the determinant of the coefficient matrix is 0. So that's where the characteristic equation comes from. It is explained in my notes, I think, as well as in the, I mean, in my videos, as well as in the book. Characteristic equation. Great. So, okay, let's look at the next question. If Roman isn't happy with my answer, please make a post there if I could explain further. I think next question in line is Chad's question. Is there a way to double check your simplification of the vectors in the linear equation? Yes, there is definitely a way. If I understand correctly your question, so once you get the solution k, once you get the k, you can take it back and multiply by the matrix and see if the answer is 0. Or maybe you can even take it back here. So once you find your k, take it back here and substitute it in here, compute this left hand side, a times k, equate it to lambda times k, and see if you get the right answer. If you missed some of the k's, this will not show that you missed. But if you didn't miss, then you will know if it's correct or not. But if you missed some of the eigenvectors, by taking those that you found and putting it back here, it will not tell you that you've missed something else that you could have also put in there. Okay. Okay, Ray is asking a question, will this be archived and uploaded afterwards? Absolutely, we can do that. I think YouTube is gonna make a copy of this thing, and then I can download it and put it on Sunlearn. It's gonna be a huge file though, but it's definitely possible to do that. I also have a software that can decrease the size a bit, so maybe I'll make use of that. Okay, so now we come to Katie Mee's question. Generally, what is a good strategy for simplifying the matrix when you have to find the determinant? Let me think about this. I actually don't know any way of simplifying the matrix for finding the determinant. The only thing that comes to my mind thinking about this question is that when we have a symmetric matrix, there is a way to not to simplify actually, and then get the answer quicker. And here is an example. So if I had something like 1 minus lambda, 2, 2, just to make sure it's symmetric, then 2 minus lambda, 3, 3, 1, 1, and then let's say 1 minus lambda again. And if I was working on the determinant of this thing, So how would we compute the determinant? Well, the way I know how to compute a determinant is we take 1 minus lambda and you multiply that with the determinant of that matrix here. And so that's 2 minus lambda. Chad, I hope you're there pointing out my mistakes. Times 1 minus lambda minus 1. And then we subtract from that 2 times the determinant of this thing here, right, of this matrix. So that's going to be 2 times 1 minus lambda minus 3. And then we have plus 3 times the determinant of this thing here, which is 2 minus 3 times 2 minus lambda. And here what I wanted to tell you doesn't work out because there is nothing you can take out as a common factor. But imagine a scenario where let's say we didn't have some terms. For example, a scenario where I'm not getting this the way I wanted to get it to. The point I want to make here is that if certain terms are not there, we could factor things out. Like, okay, let's try to achieve that. So, okay, so for example, so imagine you had imagine we didn't have 2 minus lambda there. Imagine there was 1 minus lambda here. Okay? And moreover, imagine that oh, Chad is saying something is incorrect. Okay, what is incorrect here? 3 times 2 minus 3 times. Don't see anything that's incorrect. Maybe you can make it more specific what is incorrect there, Chad. So if we had something like this and we didn't have, let's say, this term here and that term, then my point is that what you could do there. Okay, Chad is saying it should be 3 times 2 times 1 minus lambda. No, I don't see why. Yeah, okay, he apologized. So one thing you could do, you could just multiply everything out. But the problem is that if you multiply everything out, you're going to get a cubic equation. And we don't know how to solve a cubic equation. So instead of multiplying things out, you can factor things out. And for instance, we could factor 1 minus lambda out. And then we would get something like 1 minus lambda times some p of lambda, where p of lambda is a polynomial of second degree. And so, if we want to equate this to 0, it's sufficient to know that this is 0, right? Because we already know this will be 0 for lambda equals 1. And then you have to just solve a quadratic equation instead of a cubic equation. So that's the only technique that comes to mind when I see Kate in his question about simpler ways of computing these determinants. But that technique, I think, is only applicable in certain symmetric matrices. In general, I don't know of any technique. You just find the determinant and get the polynomial. And yeah, sure, if you can factor things out not to make them all. If you factor things out like we did here, maybe with non-symmetric matrices as well, as much as we can, of course that's an intelligent thing to do, because if we multiply everything out, we're going to get a polynomial of high order, and then we don't know how to solve the polynomial. So that's the only technique I know, unfortunately. If anyone knows of any other intelligent techniques that we could use, let me know or teach me, and then we can share this with everybody. Okay, so what's the next question? I think I've dealt with all the questions that's on the chat, and there is nothing on WhatsApp. Was this useful to anyone? It felt a lot of times it felt like I'm explaining something that everybody already knows. While I'm making space for more Blackboard, maybe you can give me some feedback there in the chat if I explained anything at all that was new for anyone. Okay, well, I got one thank you there. Thank you, Katie, for that. So I guess I did say something useful. Okay, so how about your background on vector spaces? I imagine that it was a bit difficult topic because of it being so much new topic. So maybe I'll point out to you some key concepts that okay, so thank you, Rowan. He also says it was useful. Yeah, so Chad says he prefers interaction as opposed to videos. The question is, how do we do that? Okay, this is one way of doing it, but now you only have interaction here one way. I mean, you can also interact with me, but with a little bit of a delay. The other thing is that, right, okay, thanks Arno for that. Yeah, so that makes sense. I actually, I must confess to you, I actually started to realize how important these conversations are a bit later on after the lockdown, when with my more senior students, I saw that the only way is for me to give them video feedback. So every time they submit a solution, there the class sizes are much less, so I can individually give video feedback to each student. And so I basically open up their solution and I discuss the solution together with a blackboard, and I talk through it, and it has been so useful. And then that's when I got thinking that maybe something like this also should be carried down to the lower years, like engineering second year. Okay, so Chad points out something I could develop on: concept of basis and concept of span. Arno says there is something called Discord that we can use to share screen. Absolutely, let's try that next time. And Teams as well. Yeah, Teams actually could be something that could work indeed. Okay, so we'll organize a Teams lecture, and then we can put it officially for everyone, because you see the problem with using YouTube is that not everybody will be able to access it, and it's kind of unfair to those students who are not able to have enough data to access YouTube. And so I was a bit hesitant with these things, and we also didn't post it officially on Sunlearn because of that problem. So what I'm doing now is considered as out of the course, so we're just doing it in our leisure time. This is not supposed to be a formal part of the material, but maybe doing a Teams lecture can be formal enough, because I think everybody will have access to Teams. I'm not sure though it's free access, but it's supposed to be, at least as far as I can understand. Okay, so let's get back to some mathematics. So the concepts of basis and the concept of span. Yeah, these are actually two very, very important concepts, and maybe we can let the little guy there rest a little bit, otherwise he's been scratching his head for far too long, and then we can bring him back again. Okay, there we go. So, let's begin with the concept of, maybe we're going to treat those concepts simultaneously. I'm going to begin with using the two-dimensional example. So when the space is R squared, many times in previous years, while I'm drawing this thing, let me tell you a little story. Many times in previous years, we would have extra classes for 5 hours long. We would start like at 5 o'clock in the evening, and then go until 10 o'clock. And then last few years, somehow I dropped that. But now our discussion today reminds me a little bit of that. I don't think we should go for 5 hours now, but we could give it a try at some point. Anyhow, so let's consider this space R squared. Now, what is a basis? So let's begin by finding some specific basis for this space. Well, the first one, the traditional one, the one that wears a tie and is always invited at all the formal occasions, is the one with the vectors being 1, 0 and 0, 1. Okay, so this is just one example of a basis. I'm going to denote it by B1, and unlike your book, which gives this curly bracket notation, which is supposed to be for sets, I'm going to give a round bracket notation, because basis is not a set, it's a sequence. But in the context of this course, we are teaching it as if it was a set, because it is like that in the book, unfortunately. At some of the videos, I think I discussed the difference between the two. If the difference is going to come up in our discussion, we're going to look into it, but for now, just let's ignore that part. So B1 consists of two vectors, 1, 0 and 0, 1. And now let's discuss why is this a basis for R squared. So what makes it a basis? And there are two things that makes this thing a basis. The first one is that the span of B1 is equal to all of the space. And the second thing that makes this into a basis is that B1 is linearly independent. By the way, if that music is too loud or disturbing to anyone, let me know. I don't know how about you, but I cannot really do mathematics under music. I mean, when it's something I already know and I'm talking about, this is no problem. But if I have to develop new mathematics, then music distracts me, because I also like to create new music, and then I'm starting creating the new music instead of the new mathematics. Anyhow. B1 is linearly independent, and span of B1 is equal to R squared. These are the two requirements in order for it to be a basis. And so let's now check that these two requirements hold for this specific B1 that we've pointed out there. Okay, what does it mean that span of B1 is R squared? What is span? Well, for an engineer, a span shouldn't be a difficult concept to understand. Basically, a span is what you can build out of the building blocks, okay? Well, I know that you're gonna think that I'm a very primitive thinker, but for me, engineering, first of all, is about building things. And perhaps, first of all, it's about building things from bricks. But now, instead of bricks, and I mean, I know I downgraded engineering too much, but of course, building things is one of the wonders of engineering. All the things we've managed to build, using some mathematics, of course, but not only mathematics, also some music, I guess, because inspiration is important in building things. So when you build something from bricks, you lay those bricks together and you put cement in between, right? Now, when you build something from vectors, the process is a little bit different, and namely what you do is you take those vectors, and in this case we have only two vectors to work with, the 1, 0 and the 0, 1. Cries in civil engineer. Okay, I'm not sure I understand Chad's jargon there. Did I say something bad or something good about civil engineering? Anyhow, so yeah, I'm not very updated with the style of jokes for the next generation. I think I'm getting old or something like that. 1, 0 is our brick, and the other brick, it does look like a brick, right? It has a square shape at least, a rectangular shape, I should say. So these are the two bricks, and to make something from it, instead of putting them on top of each other with cement, we're going to multiply each of them by scalars, and these scalars could have any value. Okay, so that's the point, C1 and C2, and then we add them. So the way we build something from vectors is that we take their linear combination. Something like this is called a wall, right? Whereas something like this is called a linear combination. I mean, this whole thing. And now a house is made by all the walls, and a span is made by all the linear combinations. So that's the analogy there. So what you want now is to put all of these linear combinations into one set, just like you would want to put all the walls into one structure, and that structure being a house, something like this, right, with a door. But we don't care about doors in mathematics because nothing has physical manifestation, so that there's no point of opening or closing anything. And how do we make this house? We made this house by putting walls next to each other, right? So now we want to do the same thing here. We want to put linear combinations, but the linear combinations, two linear combinations, are not going to be put into like one linear combination. Like two walls are not put into one wall, right? The house can distinguish the walls. You don't just squash all the walls together to make a house. You put walls next to each other, and you can still tell which wall is which, right? So that's what we want to do with this. We want to combine these linear combinations into a set, and so this set is called span. And now I'm gonna explain that notation in a moment. So basically, the objects in this set are the linear combinations, where C1 and C2 could be arbitrary real numbers. Okay. Does this make sense? Okay, so what's this notation all about? These brackets is just there to tell us that the whole object here, this whole thing, is a set, okay? And what is a set? You can think of it as a box of ingredients. The ingredients being these things, okay? So if I look into this set, if I start staring at it and examining it from outside, right? What I'm going to see there is going to be what? So let's see what I'm going to see if I open up the box and look inside. I'm going to see there something like this. 2 times 1, 0 plus 3 times 0, 1. So that's going to be one object inside the box. Another object inside the box will be 5 times 1, 0 plus 7 times 0, 1. A third object in the box is going to be 10 times 1, 0 plus 11 times 0, 1. Okay? And so each of these objects, they're separate entities, right? They're separate vectors, actually. And so this box is going to consist of all such entities, all such vectors, where the C1 and the C2 could be arbitrary scalar values. So whatever you choose for C1 and C2, for the corresponding values of C1 and C2, you got one separate object in the box. And so let's start computing these objects. So in the first case, we would get, so what is this linear combination? This is the vector 2, 3, right? And that is the vector 5, 7. And this one is the vector 10, 11. Okay? Okay, so now let's start listing them. So if I take span B1 equals, and I start listing these things, okay? So 2, 3 is there, comma, 5, 7 is there, comma, 10, 11 is there, and so on. Now the question is, what else is there? What else can be, which other vectors can be written down as such linear combinations? Some C1 times 1, 0 plus C2 times 0, 1. And the answer is, well, if I do the computation already here, look what I'm getting there. I'm getting there C1, C2, where C1 and C2 can be arbitrary real numbers. This is basically any kind of vector I can ever get on R squared, right? And so this span works out to be all of the R squared. Because any vector in R squared is a linear combination of 1, 0 and 0, 1. You don't believe me? Okay, here it is. Take any vector x, y. Now we call the C1 and C2 x and y instead. Just a change of name. Anybody is allowed to change their names, right? If I tell you now, I don't want to be called Professor Zurab Janelidze anymore, I want to be called Professor Michael Jordan, right? You cannot tell me, you know, I'm not allowed to do that just because I cannot play basketball. I tried though when I was young, but it didn't work out. I think I wasn't athletic enough or something like that. So let's change the names from C1, C2 to XY so it becomes more familiar. And then we make a remark that XY is the same as X0 plus 0Y. And that's the same as X times 1, 0 plus Y times 0, 1. Right? And there we are. You see, we got it represented as a linear combination just like the other one. It's just that the name is different now. Now this C1 is called X and C2 is called Y, but who cares about the name? So this line here, this line of calculation here, proves that the span of B1 is R squared. And remember, that was one of the requirements for a basis. If I go back now, I wanted my basis to be such that it's going to span the entire space. Okay? Now, just one minor technical issue here. When we talk about a span, we do want the thing to be a set. And when we talk about the basis, we want it to be a sequence. So here I should actually not have written B1, I should have written it in the set form. So I'm gonna make that correction to be very, very explicit in the precision of what I say here. So instead here we need to have a set version of the basis, which will be the set with members 1, 0 and 0, 1. Okay? And so the span of something is taking all possible linear combinations of their ingredients, just like when we make all possible walls out of given bricks. The bricks are the ingredients. Of course, the difference between the walls and the linear combinations is that in a linear combination we can reuse vectors. You see, I've used 1, 0 here for this linear combination for this one here with the blue arrow, but now I've reused the vector 1, 0 for this one, and that's because in mathematics anything can be reused, right? In real life, if you use a brick for a certain purpose, you can't reuse it anymore. It's already used there, and that's it. Okay, so that's the first requirement, that the span should the span of this thing to be called basis should be all of the space. And the second requirement is that it should be linearly independent, and I think you already know what that concept is, because we had a lot of discussion about this in the context of functions, discussion about linear independence. Of course, geometrically here, linear independence means that these two vectors don't lie on the same line. And we also discussed the geometry of that in the lectures. Wow, Ryan posted some very interesting picture. I can't see what it is. It looks some kind of hieroglyphs, maybe. Okay, I'm wondering to know from Ryan what that picture represents. Anyhow, so now Chad, maybe you can give me some feedback there if my explanations are good or not. So what my goal here was, in the first step of answering your request, was to explain, to give one example of a basis, and then to explain why is it a basis. So the example we gave is the one that consists of two vectors, 1, 0 and 0, 1, and we explained why it is a basis. It's a basis because it spans the entire space, and also because it's linearly independent. But now, while you're posting that feedback there, I want to give you another example of a basis. And here is another one. It's going to be a green basis. So this one was a white basis, and now we're going to produce a green basis. And so consider these two vectors instead. I'm not even going to write them out as numerical vectors, because I now want to abstract away a little bit. So let's call this thing b1, small b1 and small b2. And let's consider another b2 basis to consist of those b1 and b2. Now, how do I know from this picture that this is going to be a basis? Well, the first thing I want to check is that it spans the entire space. And I'm going to do that on a separate picture, because otherwise this picture is going to get too heavy with all the things being written over it. And the second thing I'm going to check is that this b2 is also linearly independent. But this one is clearly linearly independent because b2 isn't a scalar multiple of b1, since they don't lie on the same line. So let's agree that we understand why this is linearly independent. So to check that it's a basis, then all it remains is to check that it spans the entire space. And how do we get convinced of this? Well, in one of the groups, and actually in the group where I think it's the group where Chad has his lectures. Remember one of the rooms there, we had to travel far, and we always found a beautiful applied mathematics lecture from the first year that was talking a lot about pure mathematics. So Oh dear, my drawing got collapsed during the travel, but I know how to fix that, and I'm gonna make another copy then, so that now it's gonna look better. There we go. So let's get convinced that the green set of vectors spans the entire space as well, but this time let's get convinced of it geometrically rather than algebraically with computations with numbers. So in order to get convinced of something like this, what we want to do is to start creating linear combinations out of the green vectors. And our goal is that by taking linear combinations of these two, we're going to get the entire space. Because remember, span, let's actually write this down, span of the set of vectors b1 and b2 is the set of all possible linear combinations. So it's all possible c1 b1 plus c2 b2, where c1 and c2 can be arbitrary real numbers. Okay, so I promised you earlier I would explain this notation, and I didn't. Okay, so in this notation, well, I started explaining, but then I think I forgot to explain the rest. The curly brackets there stand for the fact that this is going to be a set, and then here we've got the objects in this set, how they look like, and here on the right hand side, after this vertical line here, we have a condition on these objects. So in this set, we're going to select objects of this form, of the form that is on the left side of the vertical line, but not all of them, only those that meet these requirements. For example, the case when C1 and C2 are complex numbers are excluded now. Yeah, I'm definitely, Daniel, thank you. I'm definitely going to give a counterexample to a basis. So this is the explanation for the notation of the span. So it's a set which has some objects inside the set. The set is a box. It has some ingredients. And when we decide what goes in the box and what doesn't go in the box, the way we do it is the following. So there is somebody, a kind of control checking person there that's going to make all the decisions about what to put in the set and what not to put in the set. And the way he's going to examine them is that, first of all, he's going to pick out this object and see if it meets the shape, if it's of this shape, right? And it's going to check if it's a linear combination. And once that object passes through that test, that it meets the shape that's on the left hand side of the vertical line, then he's going to move the object to in another hand. He has two hands, like all of us do, and he's going to look at it closer with his glasses, okay? And he's going to examine if that object having that shape now has this property. So it's the shape and property. So the left hand side of the vertical line gives us the shape of objects in the set, and the right hand side of the vertical line gives us the properties of the object. And so the object, for it to qualify to be dropped in the box, and you see he already dropped many things into the box. For these objects to qualify to be dropped there, they need to have the specific shape and the specific properties pointed out in the set definition. And as I said before, let me repeat that. Here, this green arrow indicates to the shape that the object should have, and the purple arrow indicates to, that purple doesn't look very purple, the yellow arrow indicates to the property that the object should have in order for the object to be included in the set, okay? And so, just to give some examples now, we have to design a linear combination of the B1 and the B2, and to design a linear combination, we're going to come up with one object and check that it has the necessary shape and the necessary properties. So let's pick, I'm gonna denote it with red. Let's pick this vector, okay? Okay, so now this guy here is holding the red vector in his hand. The same red vector, we've got it on the R squared. And what he wants to do is to check whether that red vector should be inserted in the box or not. How is he going to do that? He's going to look at the shape and he's going to look at the properties. So the first task is to look at the shape, and the shape needs to be a linear combination of b1 and b2. So the question is, can we find c1 and c2 that will make that linear combination equal to the red vector? And it turns out we can, and we can geometrically find those values like this. You take lines that are parallel to the green vectors and you draw them here. Okay. Now this line, and we're gonna have to zoom out here quite a bit because I want to intersect some of those lines, but they will intersect far away from where we have space to draw. So this is the miniature version of that drawing, and so when I took that b2 vector, well, b1 vector, and drew a line that's parallel to the b1 vector, okay, like that, it's gonna intersect the line that goes through the b2 vector. So here is the b2 vector, here is the b1 vector, and this line, let's call it L1, is parallel to the b1 vector, and it intersects somewhere here. Now this vector here, because it lies on the b2 line, is some scalar multiple c2 times b2. And now I'm going to do the same thing, but the other way around. So I'm going to draw a line that's parallel to b2 line, and then intersect it with the b1 line. And so if I do that, if I draw a line that's parallel to b2 and intersect it with the b1 line, the intersection is going to be somewhere here. And that vector will be some scalar multiple of b1 because it's going to lie on the same line as b1. And now if I take these two vectors, which I'm going to mark now with a different color so it shows, these are going to be yellow ones. So c1 b1 is the yellow one there, and c2 b2 is another one yellow here. And now if you look at this, by adding them through the parallelogram rule, you're going to get the red vector. Magic, right? So it turns out that the red vector is equal to the sum of the two yellow vectors, which are c1 b1 and c2 b2. And so this is when we get convinced that the red vector does have the shape we want it to have, and the shape being this linear combination. Okay, so the first test is passed. Now the red vector goes from one hand of the inspector to the other hand, and what he wants to do there is to check the properties, and the properties say that the c1 and the c2 must be real numbers. And in this expression, the way we found those c1 and c2, they are indeed real numbers. Right? We can find real numbers c1. I mean, the c1 and c2 we found from the picture are clearly real numbers. So it passes through the property test as well. Therefore, the red vector ends up being placed in the box. Okay? Would there be any vector that will not get placed in this box? And it turns out, so that's the thing that we discussed with this group in that remote room that we had used to have lecture one of the days of the week, that I can draw any vector. Instead of this red one, I can draw any other one on the plane, and it will always be possible to put it in this form. And so the conclusion will be that just like in the previous case, the span of b1 and b2 is all of r squared. Okay? So these two vectors, even though they're no longer orthogonal to each other like the traditional tie-suit version of the basis where the 1, 0 and 0, 1 vector, they were orthogonal to each other, they were unit vectors. The b1 and b2, they're not orthogonal, they're not unit vectors, but still they form a basis. Okay? So this is when you find an example in mathematics which is similar to real life, where you got these officials in real life who pretend to know everything, and then you find somebody from the street who knows as much as the officials do, and then you start to realize that there are much more people who are knowledgeable than just those who are officials, and then the world is happy because we're all knowledgeable and we can celebrate and so on. Anyhow, so the green set is again a basis, and now I've given 2 examples of basis, and now let's look at a counterexample as requested by Daniel. Okay, so in order to get a counterexample, an interesting one, I'm going to switch to a 3-dimensional space. There, I'm going to pick 2 vectors for which I'm going to test if they form a basis or not. And so one of them will be a vector that lies on the YZ plane. And so this vector is given by, now I'm going to actually pick some specific values. The x coordinate is 0, and the y coordinate is 1, and the z coordinate is 2. And the other green vector I'm going to pick will have again x coordinate 0, y coordinate 2, and z coordinate 1. Okay? And now this is my 3rd example, which actually will turn out to be a counterexample. So I take a sequence of vectors consisting of 0, 1, 2, and 0, 2, 1. And I'm asking the question whether it forms a basis or not. A basis of what? Chad, is it going okay? Are you getting any new information about basis and span, since you're the one who originally requested this topic? So I'm wondering to know your opinion about how are we doing here. So for B3 to be a basis, first of all, we need to ask basis of what? Well, we are now inside the space R cube, so we want it to be a basis of R cube. And so then we want it to span R cube, so the span of this should be R cube, and the other requirement is that B3 must be linearly independent. Yeah, these are the 2 requirements for being a basis. Okay, so let's check one by one. Let's look at the first one. We want the span to be R cube. Well, maybe let's look at the second one because it's easier. Is it linearly independent? Yay, it is, because one vector doesn't lie on the same line as the other one does, right? None of them is a constant multiple of the other one, so B3 is linearly independent. So we're good on this side here. What about the span of that thing being all of R cube? So let's actually compute more explicitly than we've done so far what the span will be. Let's compute the span of, well, it wouldn't be more explicit than what we did in the first example, but it will definitely be more explicit in terms of computation than we did in the second one, where we used geometric arguments there. So this span, remember, it's supposed to be all vectors of a certain shape, and the shape is of that of a linear combination. 0, 1, 2 plus C1, 0, 1, 2 plus C2, 0, 2, 1, where C1 and C2 are real numbers, right? And now we don't want to stop there. We want to continue this and write it out what the set looks like. So we continue this. So what we can do here, we can do some simplification in the form, right? The C1 can be brought inside the vectors, and then we can add them. So we'll get C1 times 0 plus C2 times 0. Now we have 1 times, well, C1 times 1, rather, plus C2 times 2, and then C1 times 2 plus C2 times 1, where C1 and C2 can be arbitrary real numbers. Okay, now let's do the sums there. Anything multiplied by 0 is 0, so the first entry there is 0. The second entry is C1 plus 2C2, and the last one is 2C1 plus C2, where C1 and C2 are real numbers. So now that inspector there, that's supposed to check whether something is in the span or not, is when he looks at this, he says, okay, this is the shape that the vector should have. It should have a 0 in the first coordinate, and it should have some value here and some value there that look like this, that can be presented like this for some values of C1 and C2, and the property is that these C1 and C2 must be real numbers. Okay, now the question is this going to be R cube? Well, clearly all the vectors in the span are going to be inside R cube, right? Because they're all vectors in 3D, so they've got 3 coordinates, right? So clearly everything in here, okay, so we've got 2 boxes here. One is this box, the box that represents the this set here, the span, and the other is a box that represents the space R cube. So all the vectors in R cube line here, and all the vectors in that span line here, and we're comparing these 2 boxes, and we're comparing their ingredients, right? And so if I take any vector that lies in here, that's also going to lie there, because any of these vectors are vectors in 3D. So now I want the other way around. Is it true that any vector that lies in here on the right hand side will also lie on the left hand side? And that's where we start to get into trouble, because the vector... Okay, so here is another prize question without any prize at the moment. So can you name a vector that you can find in R cube, but you definitely cannot find in the span, based on the final form that we gave to the span here, the form of the elements that we've got there? I'm gonna wait for answers. We want a vector that can be found in R cube, but cannot be found in the span. As long as anyone is still there. Maybe everybody left and I'm just talking to myself. Yeah, the thing... Oh, there we go. Chad is there after all. Okay, so Chad proposes 1, 1, 1. Thank you, Chad. Okay, so how do we know this vector is not in here? So this vector will get disqualified by the inspector to be placed in the box. Indeed, Daniel, thank you. Yes, absolutely. Any vector that will have a non-zero x component will get disqualified from the box. I like Rowan's answer very well. 1, 0, 0. That's the kind of almost like simplest thing, right? So why will it get disqualified? Because of the first step of the inspection. The form didn't match. The shape didn't match. The shape requires here to have a 0, and here in these ones, the ones that you've specified in the chat, have a non-zero entry there, specifically 1 or another value. And so these 2 things are not equal. And since they're not equal, going back here, we can conclude the span of this fails to be R cube, and therefore we get a counterexample to a basis. And now a geometric insight to this is that these 2 vectors, just like those 2 we had before, is going to span the entire y equals z plane, but nothing that's outside that plane. Anything that's outside that plane is not going to fall in the span. And so the span is not going to be the entire R cube space. The span is going to be just its 2-dimensional subspace, the YZ plane. So by this time we had 2 examples of a basis and 1 counterexample. And as you see, in all cases, we are applying the same definition over and over. For something to be a basis, it needs to be linearly independent, and it needs to span the space of which it is a basis. Now, the green vectors are not basis for the entire space R cube, but they're still basis for... okay, Sad Badet's answer there is nice as well. That's another vector that's not going to be in the in that span. So the green vectors here do not form a basis for the R cube as we saw just now, but they still form the basis for the blue subspace, the subspace of YZ plane, right? And that can be demonstrated by a similar argument that we did here when we saw that these green vectors form this a basis for r squared. So when you talk about a basis, we need to be specific about which space do we have in mind, of what is this thing a basis or it is not a basis. Because depending on the space, something might be a basis or might not be. If something is linearly dependent, it immediately disqualified from being a basis. But if something is linearly independent, it could always be a basis of some smaller subspace. And specifically, any linearly independent set sequence is going to be a basis for the thing it spans. And that should be quite easy to see, right? So imagine, let's now look at a fourth example, which will be kind of theoretical example. Imagine we had, so this is our B4. Imagine B4 was already span of something specific. So let's say span of B1 up to Bn, where, sorry, not B4, but the space S. Okay. All of that gone. Let me try this again. Imagine we are working with a space R to some power M. Let's make it for interest's sake 56 or 7 or something like that. Imagine we are working in a 57th dimensional. Yeah, you're right, Chet. There, we would have to first prove it's linearly independent for something to be a basis. So what I was trying to say here is that if I have a 57th dimensional space, and in that 57th dimensional space, I have 27 vectors, which is linearly independent. Okay. And I take a subspace of this 57th dimensional space consisting of all linear combinations of these. So I take the span of those 27 vectors. That thing is going to be a subspace of R to the 57, first of all. It means that it's going to be closed under addition and scalar multiplication. And then this example I wanted to show you here, B4. So B4, which now consists of those 27 vectors, is not a basis of R57, because just like in the previous example, you will be able to find vectors in a 57th dimensional space that cannot be expressed as a linear combination of 27 vectors. But B4, the same B4, is going to be a basis of something smaller than the entire space, and namely of the word "of" is missing here, of S. So S, being a subspace of R to the 57, is itself a vector space, and B4 is a basis of S, but not of R57. And the reason why B4 is a basis of S is quite trivial, because we need two requirements, right, for it to be a basis. First of all, that it needs to span, so S needs to be equal to the span of B4, but this is definitely the case because that's how we defined S in the first place. We took S to be the span of the B4. And secondly, we would need to know that B4 is linearly independent. And now I myself started to swap between the set notation and the sequence notation. So B4 is linearly independent because, again, we started with an assumption that it is. And so this requirement is met. On the other hand, S is a span of B4 because we took S to be a span of B4. So B4 becomes then a basis. So any linearly independent sequence will be a basis of its span, but not of something larger. And with eigenvectors, that's exactly the scenario we're encountering. So let's give one final illustrative. Actually, let's go back to this previous example. And so these two vectors, the two green vectors, could have been eigenvectors for some matrix, for some 3x3 matrix. And because they're eigenvectors, they are eigenvectors. Sorry, I didn't mean to say that. So they could have been eigenvectors for some matrix, for some 3x3 matrix, and then their span, the blue space, this YZ plane, would be something that's called eigenspace, and so these two green vectors would be a basis for its eigenspace, but not of the entire R cube, because unless there is a third eigenvector which it does not lie on that plane, which is eigenvector for the same eigenvalue. So if you've got three linearly independent eigenvectors for the same eigenvalue, then because they're linearly independent, and because linear combination of eigenvectors, as long as not zero, is still an eigenvector, then that would span the entire space, and so it will be it would have been a basis of those three. But these two will not be a basis for R cube, but it will be a basis for its own eigenspace. But if eigenspace is all of R cube, then it's not a basis anymore of the eigenspace. So that's how these things apply to eigenspaces and eigenvectors. Now let's look at some of the questions you've posted here. So Chad asking, in general, am I correct in saying given the span of n linearly vectors, I will end up with a span of R to the m? No. Unless you meant that m to be equal to n. So here we had an example. So that's Chad's question. Let me repeat the question. That if we have n linearly independent vectors, like here, we've got two linearly independent green vectors in R cube, and the span of those two vectors is just the YZ plane, not the entire R cube. Okay? So the answer to Chad's question, whether you will end up with a span of R to the m when you have n linearly independent eigenvectors, the answer is no, unless n is bigger or equal to m. So if I had four vectors, it turns out that four vectors, if they're linearly independent, and it's actually impossible to have four linearly independent vectors in a three-dimensional space, but if I had three linearly independent vectors, then it would span the entire space. But if it's two linearly independent vectors in a three-dimensional space, then it will not span the entire space. So that's answering Chad's first question. Oh, he meant n, and so then the answer is yes. So if you meant n there instead of m, Chad, then the answer is yes to your question. Next question is Daniel's question. If we have vectors a and b, and they both have non-zero x, y, and z components, a third vector would also be part of that basis, no matter what it is, right? Okay, so let's look into Daniel's question. It's a bit non-trivial question, I think. It's an interesting experience talking non-stop for a relatively louder voice for 1 hour and 40 minutes. You feel like you would want to shut up for the next 5 days or something like that. Okay. So let's look at Daniel's question. So Daniel is asking if we have two vectors a and b. So let's say we have a, b, both in R cube, and Daniel wants to have non-zero x, y, and z components for both of them. So let's say 1, 2, 3, and 5, 6, 2, something like that. A third vector would also be part of that basis. Okay, so first of all, if we have two vectors in a basis, then there is no third vector, right? We said we have two of them, so how can there be a third one? So the basis consists of vector A, vector B. There's nothing third here. I think what you might be asking is the span of B, whether any other vector will also be in the span of that thing. And the answer is no. Not every vector will be in the span of those. So if we have three vectors where none of the components are zero, then the only way the picture changes is that we move away now from the YZ plane, and instead we have those two vectors hanging out there inside the 3D space, casting shadow on the planes, right? On the XZ plane, and this doesn't cast shadow like that. It's gonna be like this maybe. So these white vectors are the shadows of the purple vectors. And so the span of those purple vectors is going to be a plane that passes through them. So it's still going to be something flat. And that's because there were two of them. So if I draw, it's difficult to draw something like this, but it will be something like that, a plane that, imagine a plane that passes through those two purple vectors. Only those vectors that are on that plane are going to be in the span of the B. And anything else outside the plane will not be in the span. And for example, you could have some vector which either has or doesn't have x component 0, not being, or definitely the vector with x component being 0, like let's say definitely a vector on, well, not every vector, but some, because this plane is going to intersect with the yz plane as well, right, in a straight line. So let's say the green straight line is the intersecting line. Then all the vectors on the intersecting line will fall, will have x component 0, right? It will be 0 something something, and so they will fall on the purple plane, but all the other vectors on the yz plane will no longer fall on the purple plane. So just imagine two planes intersecting each other, and the span of B being the plane that passes through those two vectors, the purple vectors. I think I answered Daniel's question. If Daniel, you've got still something outstanding there, please let me know. Now I move to Roman's question after that. To prove a basis is a span, do we just need to prove that a constant in R cube multiplied by the basis vectors still gives a value in the space we're looking at? Okay, so you cannot prove a basis is a span, because a basis is a sequence of vectors, a span is a set of vectors you create out of the basis. I think what you meant there, Roman, is to say that when you want to prove that your basis spans the entire space. I think that's what you meant, that when you want to prove something like the span of the B is equal to R cube. It's one of the requirements for proving something is a basis, right? So when we want to prove that, the basis spans the entire space, Rowan is asking whether is it fine if we just need to prove that a constant in R cube multiplied by the basis vectors still gives a value in the space we're looking at. No, the answer is, Rowan, no to that question. So you can have, like in the example here, in the previous example here, with the green vectors spanning just the yz plane, but not the entire R cube. So the green vector is not a basis. But if you take constant multiple of any of the green vectors, it's still going to be inside this, inside the span, inside the blue plane. But it doesn't mean that things that are outside the blue plane are also on the blue plane, right? So any span will contain all the constant multiples of those vectors, but it doesn't make that span equal to the entire space. Okay, and I think then there is another question by Chad. Would the other vector be the cross product of A and B? The cross product of A and B would be one of those vectors that's definitely not going to lie in the span of AB, because the cross product usually gives a vector that's orthogonal to both of them, right? Unless one of them was a zero vector. So the answer is yes. You've got two non-zero vectors there, A and B. And you take the cross product, it's always going to lie outside the span of AB. So that's an easy computational way of generating a vector that lies outside the span. So the answer is yes there, Chad. Okay, so if in the explanations that I made, if you still have something that you want to clarify further, please do ask me. Otherwise, we are approaching the end of our session, and so I guess it's time that we make plans for the next session. Well, I must be honest to you, I also miss interactions with you. And so if you told me that you want us to discuss mathematics 3 hours every day for the next 2 weeks, I would not say no. I would be very glad for that opportunity. But let's just try to make a plan that's going to be useful for at least most of the students. Teams sounds like a good idea, but before we move to this discussion, is it the right place to end the mathematical discussion, or there's something else still you want to ask? So I'll give you some time about that, and also take the opportunity to rest my vocal cords a little bit. So if there are no mathematical questions, then let's discuss about the teams. And I guess it's pretty straightforward. I will set up a Teams meeting. I will have to figure out how to invite everybody to it, maybe by just placing a link on SunLearn. But the big question is, when should this be organized? Is it something you want to do in a Friday session like this, or is it something? So it basically depends on when your study times are, right? Thank you, Rowan. I also appreciate that the students joined this, and I wasn't alone here talking with myself. So, what are the best study times for you that you when you would appreciate having an interaction like we had here, but maybe a better one where it can be more synchronous? Oh, Discord again. So yes, Chad, thank you very much for pointing that out. Okay, so let's give it a try for Discord. So Chad is gonna help me set up the Discord thing there. Thank you, Daniel. And with the teams, I guess we try Discord first. Let's see how that goes. And then we try the teams. The other thing is that these discussions, we can make them available for those who are not able to access them outside SunLearn, and so they can at least view the videos. So apparently there was a bot created to add all students from SunLearn to a Teams group from in Electrotechnique. Okay, so we'll try to find that out. Okay, so it seems like the next plan is Discord. Can Discord also record the video so that then we can share the video? But the big question is when. So should it be Friday the same time next week, or do you want to schedule it into different time slot? It's a pity I don't have any idea at all how many participants are here joining, because the YouTube studio on the internet that I'm using shows me still one number as a current viewer. Okay, Daniel says that Friday seems to be good, so we can keep this time. And so we'll have one next Friday. Fantastic. Okay, great. So thank you everyone for joining. We still have 10 minutes to complete our set time. So if you have any, Arnold also says Friday is good. If you have any questions you still want to ask, please feel free to do that. I will hang out here for the next 10 minutes and then I will disconnect. So Chad is going to find out about the recordings with Discord. I actually have got Discord on my desktop. I downloaded it once for trying out various things, but then I think I concluded it was too complicated and I never got into opening the software or something like that. Okay, so it was really nice to talk to you. I wonder what should we do with these slides. I guess without the video they're not much useful, but I'm gonna save them in case as well, if anyone will request them. There doesn't seem to be any more questions coming up. Oh, here we go. Chat says, I need philosophy of mathematics to end it off, please. Oh, okay. Philosophy of mathematics. That's an interesting topic. So, let's do a little bit of that. Maybe I'm going to relate this topic to the thing we have going on here while we were speaking. So what you see on your right here is the MIDI file that's being played. So this is actually a recording of that I made. It's a 1 hour piano recording that I made, and then when I make a recording, then I speed up it a little bit because I play slower than it needs to be performed. So I improvise, so I need to play smaller because I'm inventing the music as I improvise, as I record the piece. And so then I shrink the size, it becomes, speed it up, and it becomes 40 minutes out of the 1 hour. And so what you see there as a piece of information is basically a mathematical function, right? Now, what is weird about this thing is that if you look at it in terms of its graph, in terms of those black spots there, there is nothing beautiful about it. I mean, it isn't like a symmetric picture or anything like that. It seems to be like randomly arranged dots there. But now, if on the other hand you were to draw randomly arranged dots on a MIDI page, and then you were to play that as a music, you wouldn't get much out of it. So one thing that's remarkable, therefore, about music is that although the musical piece itself is a very mathematical object, what makes it beautiful and what makes the musical piece distinguished from other random pieces you can create out of the same pieces of information is not the actual mathematical encoding of it, but something beyond that. Our sensation for music is something beyond the mathematical bits used in encoding the musical information. But what is truly spectacular is that this phenomenon is shared by mathematics itself as well. So you can think of mathematics as some kind of musical piece where instead of those black dots there, or bars rather, you've got symbols, right? We've got symbols like sine and cosine and e to the x, and then when you study mathematical logic, you got some of these things which express logical principles, and these things and the set notation for brackets and so on. Now, all of these symbols are kind of objects like those black bars are on the MIDI file, but now the way they compose together to give meaningful mathematics is no way detectable by the arrangement in which these objects are placed next to each other. And so when we see a sequence of symbols placed next to each other, like for example, if I go back here, right, like this example, right, I've got a sequence of symbols here, just like on the right hand side there I have a sequence of black bars. Now the mathematics I can read out from the sequence of symbols has some meaning, but I could write the same symbols in a meaningless manner, just like I could create the black bars in such a way that there would be no interesting music coming out of it. And so my ability to recognize beautiful mathematics from the sequence of symbols, so to read off something beautiful, something that speaks to my soul, is a very mysterious phenomenon, just like my ability to recognize certain bar functions as beautiful pieces of music. And so we start to see here a very important conclusion that mathematics is not just a technical manipulation of symbols, just like music is not just some random arrangement of bars. And so this technicality of mathematics, the symbolic expression of mathematics, is similar to the bar expression of music, which is just a way for us to encode the information. But the meaning that the information portrays, the deeper story behind it, is something beyond that symbolic level, and it's at the level where our consciousness finds itself very comfortable and also useful, right? You can use these mathematical ideas for amazing things. And so the philosophy of mathematics is to be able to penetrate into the meaning of into the logical meaning of things, which you can write down using symbols, but the symbols is by far not the representation of it, of the meaning itself, because you could also write down something random with those symbols having no meaning. So penetrating into the let me say music of logic is the philosophy of mathematics. So with the ordinary music, it's the beauty of the sound, right? It's a combination of sounds, and some combinations of sounds are beautiful, and we recognize it as music. And in the same way, in mathematics, you've got combinations of logical thoughts, and some combinations of logical thoughts are beautiful, and that's how we recognize mathematics. So mathematics is the subject that studies beautiful combinations of logical thoughts, similarly to how music is about beautiful combinations of sounds. And what is remarkable here is the applications it can have. So beautiful combinations of logical thoughts turn out to be also something extremely useful. You develop a piece of mathematics, like Isaac Newton developed a piece of mathematics because he was after the beauty, and then it turned out a couple of 100 years ago you can use this mathematics to fly a spaceship outside the Earth. And so I mean, of course, music also has applications, music therapy and these kinds of things. So it is remarkable how in our consciousness is embodied the sensation of beauty, and how the sensation of beauty is aligned with things that later turn out to be useful, as if we are programmed to recognize things that will turn out to be useful. And when we recognize something to be beautiful, that's in some sense the program inside us that allows us to recognize that it's going to be useful. So that is why beauty and usefulness in mathematics are very close to each other, and that, I guess, answers Chat's request at exactly 7 o'clock when we have to end the stream. And so thank you to all of you for joining in. It was a great fun, and I look forward to repeating this next time on a different server called Discord. There we go. I made a very fancy ending there. Bye bye, have a nice weekend. And you're welcome to WhatsApp me if you have any maths questions whenever you like. If it's too many messages, I will simply not be able to answer them, but otherwise, goodbye.